Swayam Prabha. Digital India. Educated India.
So let us start with the control problem. Based on everything we have done so far, remember that we did bandits, we've done MDP planning, literally with just what you have picked up from those two modules, right? You should be able to construct an algorithm for solving the control problem, which is basically solving the full-fledged reinforcement learning problem. So how are we going to do it? We'll look today at one possible way of doing it. So the approach that we are going to put forward in this lecture is what's called a model-based approach. Okay, it's a model-based algorithm for solving the control problem. So what is model-based? Why is it called a model? What's a model? So model is a technical term in reinforcement learning. Model usually refers to an abstraction, right? A sort of data structure that you have that the agent keeps as a proxy for what it thinks is actually the MDP. Okay, so there is the underlying MDP that we don't know, right? We don't know what is the T and the R in that MDP. So let's go ahead and construct estimates of T and R. Okay, let's call them T hat and R hat. So we'll have in the agent's mind, right, table which for every state, action, next state will give a probability, right, of that transition happening. Similarly for that reward happening. And we'll populate these tables based on experience. Of course, these tables are not the real thing. Okay, we don't know what the real thing is, but once we have these tables, right, with us, which are estimates of what T and R are, then we can basically act as though, that is reality, right, and make do with that approximation for the time being. So, but as we go along, right, try and refine T and R, right, so that at least in the limit, right, they end up becoming the actual transition probabilities and rewards. So that's the idea. Okay, you have these estimates of T and R. The idea is if eventually you are able to get T hat to converge to T and R hat to converge to R, then what you have in your mind, right, as the MDP is going to be the real MDP, right, because convergence has happened to the right quantities. And if you know what the MDP is, we know what to do, right? You do planning, right? You find an optimal policy for your MDP and act according to that. So that's the idea. Okay, we try and estimate the MDP better and better and better, right? And act optimally according to our estimate. So at convergence, then we should be doing the right thing. The other aspect of doing this, okay, and this is where the bandits come in, is that we're trying to estimate T hat and R hat, right? We're trying to estimate T and R. Our estimates are T hat and R hat. What is T hat, right? For every state action, right, it is going to give you a probability distribution over next states. Okay, and the reward function is for every state action, next state, it's going to give you a number. So, reward sort of becomes easy to estimate if we are assuming that it is deterministic, right? There's a fixed number for every state action, next state. If you're assuming that the reward itself is non-deterministic, it's stochastic, right? Then you have to sort of estimate R of SAS prime as well. For either of these, if you want to get these estimates to converge, we really need to take every action from every state an infinite number of times. Same thing with bandits. Okay, if you stop exploring, right, if there's a particular state action pair that you have taken that action from that state only 25 times or even 25 million times, it's still a finite number of times, right? And whatever you saw as the consequence of taking that action from that state 25 million times could still be incorrect, okay, could still be biasing you in the wrong direction, right? Maybe with some very, very small probability all the time you went from that state to state 1, whereas there is some probability of going to S2, but it never happened in those 25 million trials. That can happen with a small probability, right? So we need to explore every state action pair infinitely often. Okay, this is where we are bringing to bear our lesson from the bandits. So the idea is you put these two ideas together, and we've already done that as well. Okay, so in the context of bandits, we spoke about being GLIE, right? Greedy in the limit with infinite exploration. So that's basically what we're going to do in this first cut model-based algorithm. You have to do an infinite exploration of every state action pair in order to be able to estimate T and R accurately in the limit. But then you also have to be greedy, right? What does it mean to be greedy over here? You have to act as though your model is correct. Okay, that's what it means here to be greedy or to sort of exploit your knowledge. So, assuming T hat and R hat are actually T and R, right? What would be the right thing to do? The right thing to do would be to solve for the optimal policy of the MDP S, A, T hat, R hat, and gamma, right? And act according to that policy. And doing that is what is here called being greedy, okay, or exploiting. So this is basically the idea that we're going to put to practice. And let me actually give you this in the form of pseudocode. Okay, you already have the conception. So this is just a way of formally writing things down. Okay, so here's our algorithm. So it's actually on 2 or 3 slides. So let's just look at one portion of it at a time. So first, this slide is just telling you how the data structures get initialized. I mean, what the data structures are and how we will initialize them. So the main data structures we have are T hat and R hat. Okay, so T hat is like a 3-dimensional array for every state, action, and next state. The idea is that it will give us the probability of going from S to S prime by taking A. Okay, initially we don't know what the probability is, right? So I mean, just initialize it maybe to 0, similarly for rewards. Model valid is a flag that I am defining. It's a binary thing to be true or false. So clearly at this point of time, our model, right, which is T hat and R hat, is not even like you've not even seen every state action pair once. Okay, so you'll have like sort of undefined quantities. So we should not be trusting the model right now. Okay, so let's set this flag model valid to be false. Model valid will become true when we have seen every state action pair at least once. Okay, then we'll have some estimate. Okay, whatever you saw maybe gives you, of course, a very noisy estimate, but at least it is something, right? But when you don't have anything, right, you'll end up sort of dividing by zeros, and it's not really legitimate. So we start off by saying model valid is false. At some point, you'll see when we set model valid to be true. Yes, what we want to eventually have is T hat and R hat, but T hat and R hat are probabilities, right? So how do you sort of directly update these probabilities? We actually need to store a little bit more information. So what we will do is make T S A S prime be the fraction of times we've actually gone from S to S prime by taking A as a fraction of the number of times we took A from S, right? Maybe sometimes you'll also go to other states. So the empirical frequency with which you're going from S to S prime by taking A divided by the number of times you've taken A from S, that is what we will define to be T hat of S A S prime. Okay, similarly for rewards. But for that, we need to keep the total number of times we have gone from S to S prime by taking A, which will get incremented by 1 every time that transition happens. And we should also have a variable just for the total number of visits of S comma A. Okay, so in fact, the semantics will be that the total visits of S A will be the sum of the total transitions of S A S prime over all S prime. Okay, so this is just for convenience. Instead of having sort of do a sum at every step, right? We will just keep a separate variable that's like the denominator for updating T hat and R hat for SA. Similarly, total reward, right, accumulated by going from S to S prime by taking A, that's also initialized to be 0. So this is just initializing these data structures which are going to get populated with experience. And we start gathering experience starting time 0, 1, 2, 3, right? So let's assume that when the agent comes into existence, that is time step 0, and the agent is in some state S0. All right. So what should the agent do? Okay, how does it go about updating these data structures? How does it take its actions? That's what's coming up on the next slide. Okay, so we are continuing from the previous slide. The agent got born. Okay, it's in state S0. And here's what it's going to do. At every time step t, okay, 0, 1, 2, 3, it first sees, have I seen enough for my model to be valid? Okay, so at some point the model will become valid, but if it is not valid, right, you really can't trust your model. So sort of simplistically, right, this is just a placeholder. What we are doing here in this algorithm is to take an action from your current state uniformly at random. Okay, you're doing like uniform random exploration up until such time your model becomes valid. Okay, you can also do more intelligent things here. Maybe you can use your model partially if it is it's available, but we are just specifying this algorithm to sort of be conceptually correct. We're not really optimizing it or making it most efficient in terms of how quickly it learns or something like that. It really suffices to do uniform random exploration, because if we have assumed that our MDP had reachability, right, it was irreducible, then just with uniform random exploration, if you do it long enough, right, you'll visit every state action pair at least once, right, in a finite number of steps. So that's what we do. But having taken an action, now we are going to get information about the world, right? So when you take an action, AT, the environment is going to come back to you with a reward and a next state, ST plus 1. Okay, so once you have that, this is the time to go and update your knowledge. Okay, and the knowledge that you are encoding is your model. So you will go and update your model and tell the model, I was in state ST, I took action AT, I got a reward RT, and I went to state ST plus 1. Okay, so how you actually update the model, this is what we will give on the next slide. But suppose at some point the model becomes fully populated, right? Every state action pair has been visited at least once. Then we have the liberty now of using the model, right? I mean, after any finite number of steps, the model is going to be noisy. Okay, it's okay. It's still something that we can use. It will help us maybe take better actions than actions that are uniformly at random, right? So if the model is actually valid, okay, at some point this will happen. At some point of time, because you explored enough, you'll have a valid model. Here's what you do: you act as though, right, the MDP you are interacting with is S, A, P hat, R hat, gamma. It is not. Okay, but the idea is you'll get closer and closer and closer as T hat and R hat start converging to the real thing. And if that was your MDP, which policy will you take? Sorry, which action will you take? You'll calculate what is like an optimal policy for that MDP. Let that be pi opt, and the action that you will take is pi opt applied to the current state, right, which is ST. So if you do that, right, then you're being greedy with respect to your model. That we know is the right thing to do, except you can't do that all the time. Okay, so remember that, let's say maybe after 100 time steps or 1000 time steps, your model became valid. Can you start being like fully greedy with respect to your model at that point of time? You can't, because after the finite number of steps, your model is still noisy. Okay, it's not guaranteed to have converged, and so it could be a misleading model, right? Just because the data was misleading, it didn't represent the MDP very well. You could be off by a little bit. Now, if you start acting optimally with respect to your approximate model, then you might be acting suboptimally forever. So that's not okay. You have to continue to do an infinite amount of exploration. We know how to do this, right? So the way you would do this is you take the greedy action with probability 1 minus epsilon t. With the remaining probability, you act, let's say, uniformly at random. Okay, so you're doing epsilon t greedy exploration. With 1 minus epsilon t, you are exploiting. With probability epsilon t, you are exploring. And we know that as long as epsilon t is it's something that integrates to infinity, right? So you can set epsilon to be t to be 1 over t plus 1 or something like that, right? You're guaranteed that you'll do an infinite amount of exploration. And also in the limit, epsilon t will itself become small enough and you will start acting optimally. Okay, so this is the sort of main slide. Okay, it tells us that we will, with experience, we will keep updating our model, which tells us more and more about the world. We will trust our model with more and more and more probability, but we will continue to explore infinitely often. If we do that, we should expect to converge in the limit to t and r. And if we've done that, right, then we'll also be taking optimal actions. So I hope the intuition comes across clearly. We are actually not going to do a formal proof that T hat and R hat will get close enough to T and R, and you will actually act optimally in the limit. Just take that as given right now. Okay, we did like a full proof in the context of bandits. The same thing will happen in the context of MDPs as well. Okay, and again, the same sort of ideas apply if, for example, you're not exploring well enough, right? If you start exploring with epsilon t being e to the minus t, then you're not exploring enough, and you will not have an infinite amount of exploration. So you might converge to a suboptimal policy. Okay. So yeah, these are things that presumably you're able to sort of tie back and forth between the bandit lectures and this one. The part that we have not described yet, which we've not filled in, is how we are updating the model after every experience. Okay, so that's what's up on the next slide. I've written it up as a separate function. Very straightforward. Okay, so what this means is that you took A from S, you went to S prime, and you got reward R. Okay, this is what has happened. So how do you update your knowledge? Well, total number of transitions from S to S prime by taking A, that has gone up by 1. So go ahead and increment it. The total visits to S and A, that has gone up by 1. So increment it. The total reward, right, aggregated over all time steps of going from S to S prime, taking A, that has gone up by R. Okay, so if R is always like deterministic, it's the same thing. Maybe you can handle this part of the code a little bit more efficiently. This is actually written assuming that R can be a random variable. Okay, and R of SA S prime should be the expectation of that random variable. Never mind. Okay, so now you have these totals incremented. So now you can go ahead and update the actual probabilities, right? So T of SA S prime is going to be the total number of times you went from S to S prime divided by the total number of times you did SA, right? So sometimes maybe you went to some other state, but this fraction, right, empirically is the probability, empirical probability of going from S, in this case, to S double prime by taking A, right? So make the update accordingly. Similarly, do the ratio for getting R hat. One thing that we need to be a little bit careful and do, right? We sort of assumed on the previous slide was that at some point of time the model will become valid. So when does the model become valid? The model becomes valid when you've done every state action pair at least once. Okay. See, the thing is, if there is some state action pair you've not done, right, then total visits for that state action pair is going to be 0, right? So you'll end up dividing something by 0, and that's not going to be okay, right? The transition probability is not going to be well defined. So it's because you're dividing by this quantity over here, right? That you basically you need this to have been done for every state action pair in order that T hat is well defined. Okay, and that's what is being done over here. If for all states, for all actions, total visits of S and A is greater than or equal to 1, which means you've been there at least once, then you set model valid to be true. Okay, and once it's true, then maybe you don't have to worry about it. I mean, this is just like a small coding trick. Only get into this loop if model is not valid. Okay, once model is valid, you don't have to check again. Okay, so I'm thinking of model valid as a sort of global variable. Remember that it was also used on the previous slide. Only if the model was valid did we trust the model and do the planning. If it was not valid, then we did uniform random action selection. Good. Okay, so there it is. Okay, we stated the reinforcement learning problem, the control problem, and lo and behold, we already have a model-based algorithm that will solve this problem. Okay, in the limit of experience, the model will become accurate, and acting greedily with respect to the model will become will give you optimal behavior. Okay, and of course you have to be GLI in the process of doing this. A couple of comments about what we just did. So the main idea of giving you this algorithm up front, right, was to tell you that it's possible to get sublinear number of suboptimal actions. Okay, this algorithm is one that will do it. But of course, we've not written the code in a very efficient way. Okay, so for example, we assume we are doing epsilon greedy exploration, right? So the whole thrust of the discussion with bandits was how you can do better than epsilon greedy, right? We did Thompson sampling and UCB and said you can get logarithmic regret. So we're not going to be getting into that. We didn't get into it as a part of this algorithm. In fact, nor will we be getting into it more seriously in the course. Sort of sublinearity will be enough for us. Of course, there's a lot of attention. There's been work on sort of showing regret bounds even for reinforcement learning. Okay, but we are not getting into that. The other thing that we sort of took very easy, right? We didn't push ourselves hard was the computational complexity of this whole procedure. So this procedure here, right? At every time step, you're doing an MDP planning step. You're solving an entire MDP, right? The one that is there in your model. We know that can be quite time consuming. Okay, so we are making the assumption that that's okay. Okay, amount of time spent sort of computing is okay. What we are really like looking at is sublinear number of bad decisions. Okay, so that gets taken care of. In practice, you might not want to spend so much time computing at every time step. Okay, so you can think of refinements to this process that makes it also computationally more lightweight. So we didn't do it, but certainly something that you can think about. Previously, right, before getting into the algorithm, we made these two assumptions. We said we need the MDP to be irreducible and aperiodic. Did we actually need both assumptions for convergence of this algorithm? We certainly did need irreducibility. Okay, so you can't really start sort of taking the right actions from a state that you're not visiting at all, right? So on such MDPs, I mean, the problem really is not something that you can solve unless you are coming back to every state infinitely often. Okay, but what about aperiodicity? That is not something that we needed over here. Okay, so we will probably need it later, but we didn't really need aperiodicity over here. Well, technically speaking, even irreducibility, we need it if we actually want to visit every state and take the right action from that state. Okay, if you're happy just staying put in one state and doing the right thing there, right? Then maybe we didn't even need irreducibility. But usually the idea is that, I mean, if there are sort of good states in the MDP, right, you should be visiting them and you should be taking good actions from there, because your long-term reward will depend on that. And if you want to do that, right, if you want to, for example, take the right action from every state in the MDP, then you need that MD to be irreducible. You can't sacrifice that requirement. Why is this a model-based algorithm? One way of explaining it is, as I told you before, a model formally is approximation. It's an estimate of T and R. Okay, that's one way of saying it. But the other somewhat technical way of saying it is the following. Okay, if you look at the algorithm that we specified, the data structure that we are having, right, in memory of that algorithm is this T of SAS prime, like a three-dimensional array, and R of SAS prime. Now, these are both three-dimensional in the sense they have, the size is S squared A, right? If you have S states and A actions, right, you have one entry for every state action next state. So the amount of memory is theta of S squared A. So sometimes the definition of model-based is algorithms that need theta of S squared A memory. So, I mean, what you're having in memory might be something semantically quite different from actual transition probabilities and rewards, right? Maybe you can think of other sort of derived quantities or related quantities that you keep in memory that don't really look like a model. But as long as you have S squared A entries, right, you can call it a model-based algorithm. We will subsequently look at algorithms that actually don't need S squared A memory. Okay, you can actually do with just theta of S A memory. Such algorithms are called model-free algorithms. Okay, so we will look at, for example, algorithms like Q-learning, very standard reinforcement learning algorithms that are model-free as we go along. Okay, so again, we've defined the reinforcement learning problem, prediction and control. We have seen an algorithm for doing optimal control in the limit. Okay, it was a placeholder just to sort of tell you that such an algorithm exists. We've not really optimized it. It's not maybe the most efficient algorithm, but that's okay for now. Okay, as we go along, right, we are going to look at different sort of design questions, engineering issues, and look at better algorithms. But this was just a starting point. This was for control. Okay.